Welcome back, everybody. We're right in the middle of this conversation about the factorization theorem. So we've done one direction, we'll recycle that and do it again. And I'll show you the other direction. I think there's some insight on like how many different ways you can think of transformation of variables. So their proof is a little bit specific to discrete distributions, but it can be changed to continuous distributions. So we'll talk through that in a second. We'll talk through what their notation means. Sometimes that confuses people unless you're familiar with set notation. So we'll learn all that. I want to remind us that we have a homework that's going to be due. I think I said this is going to be March 25th, but you'll want to get started on this because there's a number of things you need to do. You need to manage all the data that you're going to be simulating, and you need to code up 3 different methods. And then you need to think about how you're even going to plot out the results. So I have had people come in and give me 75 pages of plots for this assignment. You don't want to do that. So you want to give me something that's thoughtful. I haven't told you exactly how to plot everything. And so when we come back, we'll do a review session, and you might be thinking about that. But that's kind of one of my tasks. And sometimes I think more about my plotting than I think about anything else. You know, making the right plot and doing the right comparison so everybody can see what's going on. That can be the most important part of the paper. So I do tell you what to plot for this first part, but I don't tell you exactly how to run through this exercise, and there are pitfalls in this exercise. So I'll just, well, I'll say what one of the pitfalls is in a second. So just as a reminder, we're going to be flipping a Bernoulli coin, so just heads or tails, or if you know that is a 1 and 0, with probabilities p and 1 minus p respectively. And the goal here is to estimate this ratio, p over 1 minus p. So a fairly artificial problem, but it's set up this way to cause problems and show some differences between the different methods. If p is very small and n is small, you might flip the coin, for instance, 10 times. Let's say the probability of a success is 0.0001. It would be exceedingly likely that you would see all zeros in those 10 coin flips. So 10 tails would appear. And then when you try to estimate this using x bar, which is p hat, you would be dividing by 0. You would have 1 minus, or sorry, I guess I should have said if p was very close to 1 in this case, then you would be dividing by 0 right there. And that would be a problem. And so I want you to think your way through that, when the method works, when it fails, and try to describe that a little bit. So there aren't exactly correct answers in this. There's a lot of ways to do comparisons and to think through what's important. The first part of this assignment says, sample 1,000 data points. Actually, what we're going to do right here is we're going to sample 1,000 Bernoullis right here. P is going to be 0.05. So this is going to be one of those not fringe cases. This actually behaves rather well. And then you're going to compute your transformation. So our transformation is g of p, so g of x bar is x bar over 1 minus x bar. And that is some estimator of p over 1 minus p. So you'll be creating this 5,000 times. Each one of these g's is going to be based off of 1,000 replicates. So I'm going to sample 1,000 replicates from the Bernoulli. I'll compute p hat, which is x bar, and I'll compute this statistic, x bar over 1 minus x bar, and we're going to repeat that 5,000 times. You're going to plot a histogram of that. And so you'll plot something that looks like this from your 5,000 replicates. Then I want you to think about what the delta method says. So the delta method says something about this right here. And there's a couple different ways that you could write this out. I want to keep in mind, I pulled the n over here, but how we use the delta method is we might compute something like this. We might look at g of p, and then I'm going to have g prime of p, where g prime of p is the derivative. I'm going to square that out, and then I'm going to look at the variance of everything of my sample. In terms of p, we know what that is for a binomial random variable. That's going to be p times 1 minus p over n. So the delta method says that this histogram is supposed to look like this. And if I knew what true p is, I could compare these. And in a simulation study, you know what true p is. So you can take this normal density and plot it over this. It should look like that. No problems. So, and that's kind of a verification that this statistic is distributed according to what this asymptotic theorem says that it should be. You're going to repeat that exercise for different ends, and you're going to see how this performs, how well that histogram overlays, you know, the theoretical distribution that we draw. And so you can probably imagine already that if p was small and n was small, it wouldn't look very good. And so it's a nice thing to say something about the theory and prove this statement, which we did in class, but to see how it actually works in practice, that's what this exercise is going to help guide you through. So you're going to do those comparisons. I've changed the notation a whole bunch of times in this assignment, but it all kind of says the same thing. So I ended up writing, for instance, when I wrote out what the delta method says, I have variance of xi over on the right-hand side, and I have my n over on the left-hand side. And then I wrote this out a little bit differently. This is how you use the delta method. So it's going to be normally distributed, the thing that you're going to base your inference off of, and it's going to have that expectation and that variance. I've changed the notation on you so that you can get used to this and seeing different notations that say the same thing. And so I didn't put my n over on the left-hand side. It's in here, right here, the variance of x bar, right there. And so that's where the n comes from and everything. And we evaluate that at p is equal to p hat, and p hat is x bar. So where I see the p hats of the p's, I replace them with p hats. That's what that notation says. So you're going to be reporting back these expectations and these variances. Keep in mind, if p hat, if you estimate it to be 0, then p hat times 1 minus p hat is 0. And so you're reporting back some degenerate distribution. I'd consider that a fail of the delta method in that case. So that's probably not a great thing. So the delta method is going to fail when n is small and p is next to the boundaries. So what I want you to do is I want you to report this, repeat this exercise over and over again for different n's and different p's. And I tell you which n's and p's to use down here. So just to work through how many different simulations you're doing, you're going to have 7 of these right here. We could have enumerated more of those. And you're going to have 4 of those configurations of n. So you have 28 different configurations that you're sampling from over and over again. What I want you to do is I want you to store all those samples. Now, if you forget to store it and you generate data, new data for each one of your comparisons, I probably won't be able to tell. So, but it's not really a fair comparison. So we should be using the exact same data, not another simulated set when we compare methods across the board. So you'll be storing all of this data right here. That's probably the first thing you want to do is just build up your simulator. Store all of that stuff. So for the delta method, you'll compute E hat and the variance, and you'll see how the method performs for different configurations. Problem 2, you're going to do the same thing. You're going to use all those same samples you've had, all these different N and P configurations, and you're going to bootstrap over them. And so, and these are your bootstrap estimates for everything. And it's really just from your bootstrap samples, you're just computing empirical variance and mean formulas. So, no math. So that's the beauty of bootstrap. You can see how well that performs. You can kind of imagine that if n was small and p was small, I get a whole bunch of zeros, and if I bootstrapped over it, it doesn't really help you. And so bootstrap doesn't work that well also if the asymptotics haven't kicked in. Saying that, it might perform better or worse than delta method in some cases. And so you'll have to be you'll have to work through this and understand when one method works better than the other. So there's some potential pitfalls for the bootstrap. There are some heuristic corrections. So I will say this. Some people like to, in setups like this, is they like to add a success and a failure to their data set. So they'll take their data set of n replicates and they'll add 2 replicates to it. So that's some sort of penalization in everything. In bootstrapping, if you did that, you might not get one of those 2 replicates. So you might add those into every bootstrap sample. All kinds of heuristics. So if n is small, that's going to bias the method quite a lot. And if n is big, then it won't bias the method too much. And so you can think through that. I don't write anything explicit about that. And then the next problem, and I just noticed that I wrote problem 2 right here. So this is problem 2, this is problem 3, and this one's problem 4. I want you to do the exact same thing, but in a Bayesian context. And so for the Bayesian, you could work through and do this transformation that we did in class and work with the beta prime distribution. So for the Bayesian, p over 1 minus p is beta prime distributed. You don't actually need to know that to do this exercise. So what you could do is just look at the posterior distribution and transform it, or you could sample from the posterior distribution and transform all of your samples. And you could turn those into beta prime distributions, and if you didn't know that distribution was called beta prime, you would still have samples from it. And so you can operate that way, or you can operate explicitly through the beta prime distribution. What I would actually do, instead of doing an interior Monte Carlo sampling for like maybe the expectation and the variance from that posterior distribution, is I would probably go to Wikipedia. And I would probably look up what a beta prime distribution is and look at what its expectation and variance are. There are going to be functions, the hyperparameters in your prior and your data. And you can compute those explicitly. So look those up maybe in a textbook or Wikipedia, and it will save you computation. So if I run an interior simulation over all these simulations, it'll take a lot of time. So again, things that I haven't written down here, but you can think through it and try to exploit strategies that speed up your code. So you'll be comparing the Bayesian answer to all of those other 2. And you're going to report them in the context of different n's and p's, how they behave. So there's pitfalls for all 3 of the methods, and you'll explore those. I will kind of point out some pitfalls right here. Sometimes the expectation and the variance doesn't exist. So there will be conditions if you used alpha and beta in the beta prior. So I recommend using a beta prior that's half and half, but you don't have to. You can use any prior you want, just as long as you show the impact of your choice. So some things will help you so that there's not division by zeros or an expectation exists, but you'll probably bias your answer to get that. So for beta half-half, using that as a prior, the expectation and the variance of that beta prime distribution won't necessarily exist. But the posterior does exist. The full distribution exists. It exists no matter what the data looks like. So you're going to get a posterior distribution. And in some cases, you'll get an expectation and a variance. In some cases, that distribution will exist. It will integrate to one under the distribution, but the expectation and variance does not exist. In cases like that, I don't see that as a failure of the Bayesian method. I see it as a failure of what you're wanting to report. And so instead of reporting expectations and variances, you might report something entirely different. So for instance, what I might report is I might report like a frequentist quantity, how often my intervals cover the truth. And I might report that back. And for all 3 of these methods, I could do that. I could build a bootstrap confidence interval. I could build an interval off of the delta method. Obviously, in the case where 1 minus p is 0, that you can't. And I could report back frequentist coverage. And if you wanted to do that, that's fine. Saying that, if I wanted point estimates to describe that Bayesian posterior, I could give you the maximum of that distribution. And a maximum of a posterior distribution is called a map. It's a maximum a posteriori distribution estimator. I write that down here, so you can look that up. I don't explain all of this in this assignment. So if there are terms that I'm introducing to you and not telling you exactly what they are, what I'm intending is that you look them up and see what those terms are. So a Bayesian in this problem could report back an interval and a map estimator. And so you'll be thinking through all of this. So you'll try writing this up, I would say, I say, try not to write up more than 5 pages on this. I don't know if I actually say that. But let me just say it now, that probably not more than 5 pages of write-up is necessary for all of this. But that'll take you some time as well. So get that simulator started, start cooking up those different methods, and then start analyzing everything. And you want to think about the results before you start writing your report. Okay. And if you guys need help on it, I'll give you some help once we get back from work. So that's all there for you. I'm going to guess this is going to take an average student minimum of 15 hours. So you're welcome. This will be a good experience. Any questions about that? Cool. You also have some problems that are due on the 14th, and they'll walk you through some of these sufficiency principle exercises. Okay. Let's jump back into the factorization theorem. So, just for our visitors, a sufficient statistic has all the information about the parameters. So in the context of our general examples, the data is denoted as x, and our parameter space is denoted as theta. So just looking at a couple examples, if I'm Bernoulli coin flipping, P is theta. So if I'm looking at this uniform distribution, maybe there's this parameter, I called it theta earlier in the class, so I'll stick with theta. It's the boundary of the uniform distribution. And for a Poisson distribution, it's that rate parameter, is theta, lambda. So a sufficient statistic has all the information about the parameters. And we kind of talked about a different aspect of sufficiency, and this is what I tested you on Wednesday, that if you ended up looking at the distribution of your joint, and you ended up dividing it by the distribution of your sufficient statistic, this should be a constant with respect to theta. And so when we thought about that, and we proved this in the context of the 2 experimenters that they presented in the book, but I explained this a little bit differently. And I said, essentially, as a function of theta, these 2 things have exactly the same shape. So while they're different distributions, they have identical shapes. So let's just look at this example one more time to give us some context when we go to prove this. So for the Bernoulli example, we've got our joint distribution. This is just going to be product 1 to n fxi given p. And these things right here are just p to the 1 minus p raised to their indicator functions, xi, 1 minus xi. So if xi is 1, this is p, that's 0, so that's 1. So if xi is 1, that function is p. If xi is 0, that function is 1 minus p. And so it's just reporting back these probabilities. So this just looks like this. Product I goes from 1 to n, p to the xi, 1 minus p to the 1 minus xi's. And I can simplify this and write it down like this. Sum of the xi's, 1 minus p, n minus sum of the xi's. So that's just a joint Bernoulli distribution. So we know what's sufficient because we've studied this example a lot. So, and we can verify what's sufficient. So x bar, the sum of the xi's divided by n is sufficient. And we can verify that by working out its distribution. So let me work that out here. I'll just write it down here. Sum of the xi's, in terms of the data, it's only coming in through sum of the xi's. So I can divide by n, it's still a function of that, so it's still sufficient. This is Bernoulli, or binomial, with parameters n and p. Usually we don't think of n as a parameter in the model. And so what does this look like? Our distribution over sum of the xi's is n choose sum of the xi's times p to the sum of the xi's, 1 minus p, n minus sum of the xi's. So that's a binomial distribution. If I think about this problem in the context of p, and I work out this ratio right here, so I'm just going to write this down with a p, change that, this is still x, and this thing right here, t of x, our sufficient statistic, is sum of the xi's. So if I take the ratio of these two distributions, this is p to the sum of the xi's, 1 minus p, n minus sum of the xi's, divided by n, choose sum of the xi's, p to the sum of the xi's, 1 minus p, to the n minus sum of the xi's. We've done this a whole bunch of times. This is just the ratio of that thing, and these things have the same shape, so they supply the same information about p. And that's the way I usually think about this. So this is just 1 over this binomial coefficient. So this whole idea that this ratio is constant is basically telling you that their likelihood functions are the same. And so likelihood functions are defined up to proportionality. So they supply the same information. I'll say this a little bit differently when we come back from the break and we study the likelihood principle, which is built up from the sufficiency principle. So that's a sufficient statistic, and that's how you verify it's a sufficient statistic. Factorization theorem does something a little bit different for us. It says if I can write the joint distribution is a factorization between the sufficient statistic, a function that contains the sufficient statistic and the parameter, and I can factorize it away from some function that just contains the data, and I can never factorize this away from theta, our parameter, then t of x is sufficient. And so, and in the context of our example, then I could just write down our likelihood function, 1 minus p to the n minus sum of the xi's, and you can verify that I can never factorize this away from p. And I can't do it over here either. And so sum of the xi's is always entangled with p. And so that's the sufficient statistic. Okay, let's prove this statement. So this is how I actually verify that something is a sufficient statistic, just by doing that mental factorization. So, proof. We'll look at these other examples in a moment. So we did the if direction already. So if t of x is sufficient, then I can just write out f of x given theta. So this is our original model. If I know x, I know t of x. So we're getting comfortable with this step, that t of x is just a function of the x's. So if there's a probability model for the x's, and they're given to you, then I can compute the t of x directly. There's no stochasticity involved in that. So if I knew what the xi's were in my Bernoulli model, I could sum up all of my xi's and have the sufficient statistic. And that's deterministic at that point. So I can write this out like this. F of x given t of x and theta times some distribution over t of x given theta. So just as a reminder, this ratio right here is f of x given t of x and theta right here, because I can write in the t of x right here and do the exact same thing. And if the t of x is sufficient, so here's where we're going to use this, then this is not a function of theta. All the thetas cancel out, and it's really that ratio. So those are gone. And so this is f of x given theta times f of t of x. Oops. This is f of x given t of x. This is f of t of x given theta right here. So in this constructive proof right here, these need not be distributions, but the way we prove this in the forward direction is just presenting a factorization that we know exists. So in this case, this is h of x, it's a probability distribution, and this is gt of x. And that's a probability distribution. gt of x given theta. So the factorization exists. I want to point out that this thing right here just involves the normalizing constant. So usually we're thinking about that. Maybe this thing right here might be the normalizer. Let's do the other direction. This is the harder direction. And I'll present it the way they do in the book, and then I'll say a few things about generalizing their proof. Okay, so if the factorization exists, and what we'll prove from this is that t of x must be sufficient. So if the factorization exists, I can write down f of x given theta is equal to g t of x given theta times h of x. So that's the factorization that we're talking about. So it exists because I say it exists. Whatever this is has to be sufficient, and that's what we'll prove in a moment. So I'm going to look at the ratio between these two things, and I'm going to show that that ratio is a constant, is a function of theta. And so we'll look at this ratio. F of x given theta, and we'll compare it. And don't write this down yet, because I'm going to change it in a second. I usually do this. So I usually write the same f everywhere. And I mean they're totally different distributions, they're just functions. And so we're going to be a little bit more careful about this. I want to be specific that this f is not that right here. So I'm going to change this. I'm going to call it q. I think what they use in the book is a p right here and a q there. So, but these are different distributions. So q is the distribution over the sufficient statistic, and f is the distribution over the original replicate from f. So the joint sampling distribution. And so we already know that we can write this down in the numerator because the factorization exists. I can just write down gt of x given theta h of x. And then the book writes something down. And they do this in one step. And they say, this is by definition. So they end up saying this denominator right here, you can define it using this notation. This is going to be y given t of y is equal to t of x. I should probably make these caps. And then you write down that this is going to be f of y given theta. And I want to talk about this step for a moment. So the book just says definition, by the definition of a transform random variable, it's just this thing right here, where this is a sum over the original sampling distribution. The key point is this f right here is that f. They're the same distributions. And I remember the first time I looked at this and I thought, why is that true? It must be pretty simple if they're just saying by definition. So this is one way you can define a transformation of random variables. Keep in mind, they're specifically saying this is true for discrete distributions, and that's because of the sum. If you want to generalize this, you could take your sum and write it out as an integral sign. So I'll do that. Integral. And I'm going to integrate over y. Right there. So if y was continuous, I would just replace everything with an integral. I prefer that. And then I say, well, sums are integrals, and it's a type of integral. So if this was a point process or something like that, you might not have a Riemann integral. You might have some other type of integral. You might have a Lebesgue integral sitting right here. And so we'll stick with our summation notation because that's what they use in the book. But it doesn't really matter. You're just going to integrate over this function, whatever that means in terms of the space that the y's live in. Let's look at a discrete example and see why this is defined to be that. Let me just ask real quick, is it obvious why this is that? So this says right here, in terms of set notation, this says the set of y's such that the sufficient statistic on y is equal to the sufficient statistic on x right here. So this t of x right here is defined for us. So we take the data upstairs, this stuff, we just computed sufficient statistic. So in the context of our Bernoulli example, this would just be sum of the xi's. So I'm going to sample all of my different y's, different values of everything such that my sufficient statistic is equal to the sum of the xi's. So in the Bernoulli example, what this notation is saying is I'm going to look over all the collection of vectors of size n such that the sum of xi's is the number of ones in that vector and the rest of the elements are zeros. And I'm going to look over every permutation of those. And I'm going to sum those up over that set. So this is the collection of 1, 0 vectors such that the ones sum up to sum of the xi's, which is defined through that x. Let's look at an example of why this makes sense. So the size. Example. Let's just think about xi's being dice. So I'll just give them some faces, the traditional faces, 1, 2, 3, 4, 5, 6. And each one of these has probability of 1/6. So this happens with probability 1/6. That happens with probability 1/6. They all happen with probability 1/6. So this is just a roll of a fair die. And I'm going to consider a transformation of this. So I'm going to say we get to sample 2 of these. So I'm going to sample 2 rolls of a die. Each die can have values 1 through 6, each with the same probability. And I'm going to consider this transform. Something pretty easy. I'll just add them together. And this is probably the way you learn transformation of variables the first time. So they'd have you enumerate all the different possibilities of this. Let's do that real quick. So let's look at something specific. Let's look at y is equal to 7. Now, I could look at the probability distribution of y by computing the probability distribution for this sum, and you could probably do it and work out what that transformation is. And you probably could use a more complicated formula than the way I'm going to present it right here. But instead of working through the probability distribution of y, I can just think about the probability distribution of x's. So that's actually the definition of a random variable. So if I want to know the probability distribution of y's, then I invert back to x space, and I think about the probability distribution of those x's. So if that inverse mapping exists, and I can figure out the probabilities of those original elements, then that new thing is called a random variable. That's the way they'll teach it to you in a measure theory class. Let's look at the way they teach it to you in your first stat class. So let's just think about this example. Y is equal to 7. There's a few possibilities for this. And I can think about the different enumerations of x1 and x2. And I can think about their probabilities. There are joint probabilities of seeing these two things. So I can get a 7 if x1 is a 1 and x2 is a 6. x1 could be a 2, x2 could be a 5. I'll just write all these out. So those are all the possibilities. And I can figure out what the probabilities of each one of these things are. So remember, I'm not thinking about the probability of y directly, but I'm thinking about the probability distribution on the x's. So by independence, each one of these has probability 1 over 6. So that's going to be probability 1 over 36. And each one of these tuples has the same probability, 1 over 36. And I add them all together, and I'm going to get 6 over 36. So that's 1 over 6. So the probability of seeing is 7, and that's the highest probability of it, is 1 over 6. How did I get that? I didn't think about the probability distribution on y. I thought about the probability distribution on the x's in its joint probability distribution, and then I summed over all the possibilities. That's what this says. So this is saying, instead of thinking about the probability distribution of your transform, think about the probability distribution of your original random variable, that's f. This is that same f, and sum over all the collection such that they have the same constraint right here. So again, in the context of our Bernoulli example, this would be summing over all the possible vectors of 1s and 0s such that the sum of the 1s and 0s is equal to whatever the sum of the 1s and 0s are in that original vector. So this is a simple idea. The notation, you just have to work through and understand what it means. So this would be a little bit harder to explain if I used a continuous random variable. But you can now extend this to a continuum or anything you want. So now the proof is easy once you get past this step. You just slow down for a second. Any questions about that? Or did the example clarify it for you? Good. Okay, now everything is easy. So this is just g, p of x, given theta, h of x, divided by sum over that collection with this constraint built in. And instead of writing down f, I'm going to write it down in terms of the factorization. So this is going to be g ty given theta h y. So my random variable's name is y, but the function distributing it is f, which I can factorize. And keep in mind what this constraint says. So this constraint says that ty is equal to tx. So in terms of the Bernoulli context, this, no matter what those vectors of 1s and 0s are, they all sum up to the exact same thing. So this is constant in that formula. So this is Tx. It's a constant, it doesn't change. And so I can factorize this thing out of the sum. And this looks like this. G of Tx given beta Hx over, I'll factorize this out. I'm going to write it in terms of G of Tx. I could have written it down as G of Ty, but I know what the constraint is. G of Ty is equal to G of Tx. However, the y's themselves are not constant. This function t is the constant thing. And so this is the sum over that. Cancel, cancel. And now this is just this ratio of things that don't involve theta.
Did you purposely write down T of y equals T of y?
I did not purposefully do that. But yeah, that is true, isn't it? If you'd like a sheet for your next midterm assignment, a cheat sheet, you can write that one thing down. So I'll just write down the last bit. H of x over sum of the hy's. I'll just write down the notation for completeness. So this is just the ratio of your normalizing constants. That's what it is, and more importantly, it doesn't involve theta. So theta is not in there. And so we've just shown this is a constant with respect to theta, and going back to our earlier definition, that means T of x is sufficient. And so we're done. I'll just write that down. Constant with respect to theta. So T of x is sufficient. And now we have both directions of our proof. And that's really what I'm doing. When I look at a model, I'm mentally factorizing it and seeing what I can factorize away from theta. So I'm just running through millions of calculations real quickly, and then I can discover, oh, maybe it's the sum of the xi's or something that I can't factorize away from theta. Let's look at an example. We've seen this example already and how it all plays out. Let's look at this example. So this is kind of weird. This example that we started with, where I have a 0, I've got a theta, and this is a uniform distribution between 0 and theta. So the height of this is 1 over theta. And the xi's show up in here, uniformly distributed. And so maybe we want to recognize the sufficient statistic. Now I told you on the midterm on Wednesday what the sufficient statistic was. And I told you to verify its sufficient statistic. And hopefully you were able to do that. Everything should cancel real nicely. Technically, you need to work out what the distribution of the max is to be able to do that. And so you can do that for the uniform distribution. I think I asked you to do it for the first part of the problem. I think I asked you for the minimum, just so you can explain to me you can do 2 fairly trivial things. So, and if you can't do it, study up on it. I'll give you an opportunity to make up those midterm points later on. Let me grade the midterm first. Okay, so what does this function look like? The function, and here's where a lot of people make a mistake. So I'm going to write it out wrong first. And then we'll write it out correctly. So I didn't say this, but all of these examples I'm using in my ID example, although nothing needs to be IID, I just need to write down the joint distribution for everything. I can write it down like this. Somebody help me out real quickly. What is this? One over theta, right? So this is going to look like product. I goes from 1 to n, 1 over theta. This is 1 over theta to the n. There's something wrong. So this is my third biggest pet peeve. When I ask somebody to write down this joint sampling distribution or the likelihood function, I'm thinking of this as the likelihood function because I'm thinking about its dependence on theta. So I'm thinking about it as a function of theta. The wrong part is there's no xi's in here. And so when people write this down, this should glare at them. I didn't use the data. So how do I fix this? Yeah, this boundary condition. So these problems get a little bit harder when theta is on the boundary. And we need to include that in this specification right here. So I need to include an indicator that says the relationship between xi and theta, and it's really that bounding term that is expressing that relationship. And so I'm going to write this down is the indicator function that the xi's are less than theta. I could write bigger than 0. I find it a bit superfluous to do that. And so usually I'll just write this down as xi is less than theta right here. So this is just a 1 or a 0. This happens if xi is less than theta, greater than 0. And this is otherwise. So and I need to keep that thing. So this looks like 1 over theta to the n, but I've got this product of indicators. And I want to think about what it means. It means that all of the xi's are less than theta. So it says all xi's are less than or equal to theta. And that's happening because I have this product term. So if this is a 1, once I product across those indicators, it means every single xi was less than theta. So what does that really mean? This means the maximum of my collection of x's, that's less than theta. So if the max is less than theta, then all of them are less than theta. And so I can write this out like this. xn, well that's the max, using our order statistic notation, is less than theta. And this is what you need to realize. So this problem is a little bit elusive the first time you see it. So this is the only part that involves the data and the parameter. So I could have written it down as a product of all of the xi's being less than theta, and that would tell me that the xi's themselves were sufficient. But writing it out this way tells me that the maximum is actually sufficient. So any inferences you do on theta should involve the maximum, and probably only the maximum. We'll talk about in chapter 7 what you do with it, because there's a lot of different things you can do with the max. So let me just ask the question in terms of the factorization. So this is my F, my joint sampling distribution right here. I can write it out like that. What's G in terms of our factorization? G involves the sufficient statistic and the parameter. It's kind of all of this, right? It's the whole thing. Now, I wish they wrote this out a little bit differently, because this is a function that just contains theta. And that doesn't help us. It's only the part that contains the sufficient statistic and theta. So I wish they wrote the factorization out as another function that just contains theta. Maybe we don't need to stare at that, but that's not the way they write it out. So this is technically a part of G, but this is telling us something about the shape of this function. We'll be coming back to it later. So it's saying it's a decaying function as theta gets bigger. So it places more mass on smaller theta so long as that constraint holds. What's H? It's 1. So times h of x, which is equal to 1. So h can be a constant. So h doesn't have any information for you. So I think we'll pick up next time We'll talk about the Poisson example, and then we'll jump straight into minimal sufficient statistics. So that's the maximum reduction you can get from your sufficient statistic. Obviously, for this example, the maximum is the minimum dimensional sufficient statistic because it's one-dimensional and data is one-dimensional. I'll give you a formal definition of that, and we'll start out with the Poisson example when we get back from break. Thank you, guys. Enjoy spring break. Stay safe. And I'll see you when you get back.